Alright, welcome. So, in this video, I'm about to do physics, practice 2.1e on projectiles. Now, I'm going to go through this entire packet of notes and homework that he gave us, and I'm going to kind of explain it as I go, because I know a lot of people was having trouble with physics, and I was as well. So, I'm going to go through it, and you can follow along. So, question 1 states, the question is about projectile motion and the use of an energy argument to find the speed which is thrown stone lands in the sea. No, that was just a bunch of gibberish, so let's actually go on to the question. Point P on the diagram is the highest point reached by the stone, and point Q at the same height above the sea level as in point O. Alright, at point P on the diagram, draw arrows to represent the acceleration and the velocity of the stone. Okay, so at point P, this is point P, the acceleration of the stone. So if we think about it, at the vertex, the acceleration is just gravity pulling down. So the only acceleration acting on it is the force pulling it down. So this would be A. And then the next, the velocity of the stone. As Mr. Putnam said multiple times, the velocity of the stone to the right never changes. If it's going, let's say, 2 miles per hour this way, then I'll still be going 2 miles per hour when it's here, or when it's here. So, the velocity here is this exact same. So label this V. The acceleration is going down, and the velocity is going to the right. Alright, so let's go on to the first actual problem. Now, when I like to start off doing a physics problems, I usually label everything in the graph that is given to us. So, Anita stands at the edge of a vertical cliff and throws the stone upwards at an angle of 60 degrees to the horizon. So, this is her, and she's throwing it at 8 meters per second at a 60-degree angle. So that's what we know right now. Let's keep reading. The stone leaves Anita's hand with a speed of 8 meters per second. The time between the stone leaving Anita's hand and this hitting the sea is 3 seconds. So that's another piece of information. From her leaving the hand to hitting the sea. So let's just extend the sea out. This entire process takes 3 seconds. And 3 seconds. The acceleration of free fall is 10 meters per second squared. Now, another thing I like to do when I start a graph is label our axes. So, up would be positive, and down would be negative. So, the acceleration of free fall is negative 10 meters per second squared. And all distance measurements are taken from the point where it's leaving her hand. So, after this point, that's where all the measurements are going to be taking place. So, using those constants that we know, let's continue on to the problem. Ignoring air resistance, the maximum height reached by the stone. So we're looking for a height. Now, in terms of height, we're going to have to be looking for the vertical vector. The vector that's going up and down. Because right now, we have the velocity of the rock going sideways, as you can see here, 8 meters per second. But we don't necessarily have it going straight up. And that's what we have to find first, before we find the height reached by the stone. Now, it's really simple to find the height. It's just trigonometry, as you can remember. So, ka, toa. Now, we have to pick the right one that we need in this case. So, height. Let's just draw a little triangle that we have right now. So, copying this triangle, we know that this vector is going sideways is 8 meters per second. We have no idea what this is, yet we do know what this angle is. This angle is 60 degrees. What we're trying to find out, though, is the vertical vector, the vertical velocity. So, if we add that to our triangle, that's the opposite side. That's the opposite side. This would be the adjacent side, and this would be the hypotenuse in our triangle. So, at 8 is our hypotenuse. We're trying to find our opposite side, because this would be our height, our vertical velocity. We would use so, or sine. So, sine equals the opposite over the hypotenuse. So, the sine of an angle equals opposite over hypotenuse. We know what the sine of the angle is. We know what the angle is. It's 60 degrees. So the sine of 60 equals opposite over hypotenuse. Hypotenuse, we already know to be 8. So we can just scribble this out and write 8. So we have to get O by itself, because that's this. That's the O. That's what we're trying to find. All we have to do is multiply by 8, and then we get 8 times the sine of 60. So, if we turn on our calculators, and we do 8 times the sine of 60, we get negative 2.41. Now, if you get a weird number like I just did, if you get a super weird number, check your calculator if it's in the right mode. So go to mode, and go down to radian. If it's in radians, it's in the wrong function. So go to degree. Enter. Now it's in degrees. So, going back and doing the problem again. 8 times the sine of 60. We get 6.9. So this equals 6.9. That's another new piece of information. So this vertical vector right here is going at 6.9 meters per second. Now, what were we originally trying to find? We were trying to find the maximum height reached by the stone. Is that the maximum height, 6.9 meters per second? No, that's just the vertical velocity. So, using this information, you know what we have to do? We have to put it into a SUVAT equation. So, let's take another sheet of paper and write SUVAT. So, let's see. We are trying to find the height. So we're trying to find the maximum height, that, the vertex, by the stone. Now, when we're using SUVAT, we can't find arcs. Like this is an arc. What we can find is straight up velocities or straight to the side. Now, if we take this, let's say the ball is right here, and she throws it up at 6.9 meters per second. Sorry, meters per second, because it's the velocity down in acceleration. We're trying to find out the maximum height. So, h. when the velocity at here, the velocity at the very top would be 0, because when you throw something up, it stops just for that instantaneous moment. This velocity is 0. It's nothing. As you throw it up, the velocity is 0. So, velocity is 0 at the point. It starts out at 6.9. Hey look, that's one of the SUVAT variables. And we're trying to find the height, the displacement. We have our current velocity, which is 6.9 meters per second. And our original velocity right now is, that we're trying to find, that it will initially be at the end, is 0. Our acceleration, we have to look at our own problem at that. Usually it's 9.81 meters per second squared. However, in this problem, they want us to regard it as 10. Now remember, we stated that down is a negative, so don't remember to forget that it's negative 10 meters per second squared. Don't forget. Our time isn't really relevant in this problem, so I usually like to scribble that out saying that there's no time. They didn't give us a time. There is no time. Now we have to find a formula. What I usually do, because finding formulas is hard. It's really hard. What I do, I take a flashcard like this, and write down all the SUVAT equations, and I look for the variable that's missing. So in this formula, there is no S. In this formula, there is no V. In this, there's no T. In this, there's no A. Using this knowledge that I just acquired, look at the variable that you're missing, T. Look at the formula that does not have T, this one. So you're going to have to use this formula. Really simple. We don't have this. This formula doesn't have T. So we know we have to use this formula. So let's write out V squared V squared equals U squared plus 2AS. Now with our variables, let's just plug it in. Our V is 0 squared, which is just 0. Our U is 6.9. Our acceleration is negative 10. And we're trying to find our S. So knowing this, what we have to do, let's just do our 6.9 squared right now. So using our calculators, 6.9 squared is that number. 0 equals 47.61 plus, and let's just do this right now, negative 20 times S. Now, we have to subtract this in order to get S by itself. So let's subtract 47.61 negative 47.61. So our problem ends up being negative 20 S equals 47.61. The negative. Don't forget the negative. Divide by negative 20. Divide by negative 20. So our S ends up being, using our calculators again, negative 47 divided by negative 20. Negative 2.38. So Mr. Putnam wants us to use two significant figures in a lot of his problems, so that's what we're going to do. Oh, negative. I forgot to put a negative on the 20. Don't forget to put a negative. It should be positive. So S equals a positive 2.4 meters, because this is the displacement, remember? 2.4 meters. So if we remember originally, we were looking for the height. So that means at 2.4 meters, the ball is at the vertex. The pen is at the top. At 2.4 meters, the velocity is 0. The maximum height reached by the stone, 2.4 meters. Alright, next we have to find the horizontal distance. Now you might think, oh, we have to do this entire process again, taking the SOHCAHTOA, for doing the entire SUVAT, but don't worry. It's actually really simple. We still have to do a little bit of math, but it's not that bad. So, horizontal distance, we're trying to find the horizontal distance. Now, you might be asking, what is that? So let's go back here. This is the vertical velocity. What's the horizontal velocity? It's just right here. The horizontal velocity is this. This is the horizontal velocity. So we just have to find this as well. Remember how we found this one? We used this in SOHCAHTOA. Now, I know, and a lot of other people know, that you can just use the ka next. So just replace the sine with the cosine to find the adjacent. Let's actually go through it, because some other people might not know how to. So 8 times the cosine of 60 equals the opposite, the adjacent. So that's the adjacent. Now, if you do that in your calculators, 8 times the cosine, calculator will focus, 8 times the cosine of 30 of 60, we get 4. Now, if you don't understand that, it's really simple. If you draw another triangle, this is the adjacent side, this is 60, we already know that this is 8. So we have to find the opposite, the adjacent side in ka. So it's just adjacent over hypotenuse, a over 8, just like this, a over 8 times 8, it's just 8 times the cosine of 60. Simple. So this equals 4. So here we know that it's 4 meters per second. Now that's all fine and dandy, but we're trying to find the horizontal distance. But if you think about it, the horizontal distance, so it's taking 3 seconds, right? You're going 3 seconds at 4 meters per second. Every second, you're going 4 meters. 4 meters. That's a second. Another 4 meters. That's a second. Another 4 meters. That's a second. So you're going 4 meters per second for 3 seconds. 4 times 3 equals 12. See? You're going 12 meters. The horizontal distance traveled by the stone. It hits the sea at 3 seconds. It's going 4 meters per second. 4 times 3 is 12. Alright. Let's move on to question 3. This question is about the trajectory of a golf ball. That was great. Here. So if we move on, let's read the problem and let's show in our graph what we know. So step 1, always label. I want my up to be positive and I want my down to be negative. Okay, let's see. The initial horizontal component of the velocity of the ball is 20 meters per second, and the initial vertical component is 30. The time of the flight between A and D is 6 seconds. Oh look, new information. So from A all the way to D, that is 6 seconds. A resistance is negligible and the acceleration of free fall is, oh, here we go. So we don't use 9.81, we use 10. Because it tells us to do 10. Normally we would, but it tells us to use 10. Okay. A. Maximum height reached by the golf ball. Oh, well we just did that in the other problem. Maximum height reached by the stone. What did we do? We took the velocity up 6.9 meters and we multiplied it with our acceleration of negative 10, knowing that our velocity would be 0 at that point. Because remember, when you throw it up at the vertex of that, at the very top where it starts going down, the velocity is 0. So that's simple. So the maximum height reached by the golf ball, we'll have to find the vertical velocity up. So we had to do SOHCAHTOA. Oh wait, they already give it to us. They give us the vertical velocity. It's 30 meters per second. Well, that was easy. So let's take out a piece of paper. Let's write our SUVAT, our displacement, our initial velocity, our final velocity, our acceleration, and our time. So we're trying to find our displacement. We're trying to find the maximum height. So let's write a question mark right next to that. Our initial velocity. What's our initial velocity? 30, yeah. It's 30 meters per second because it's being thrown up at 30 meters per second. What's our final velocity? So we're trying to find the maximum height. So the velocity would be 0. And whenever you're on Earth or any body, you're going to have some sort of acceleration down. Remember, it's a negative. It's going down at 10 meters per second squared. Because that's just gravity. And time, we don't know what time is right now. It's crazy. So bringing in our SUVAT formulas. Remember our quick trick? We don't have time. Let's look for an equation that doesn't have time. Here it is. This is the equation. Let's write it. V squared, our final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. Now, doing some matherinos, our velocity is 0, our original velocity is 30 squared plus 2 times negative 10, and then we're trying to find our s. So 0 equals 30 squared is just 900 plus a negative 20s. So we subtract 900 from this side just to get this alone. So negative 900 equals negative 20s. Now it's just simple. Divide by negative 20, divide by negative 20. S should equal negative 900 divided by 20. I just know that's 45. Because you can just cross out these zeros. 90 divided by 2. What's a half of 90? 45. So we just found out that this is 45 meters because this is displacement. So after doing all of that, we found out that the maximum height reached by the golf ball is 45 meters. Okay, that was simple. Now we have to find the range of the golf ball. So, range, what's that? If you've never heard of the range, that's just a really, really, really fancy word for saying the distance. So the distance from A to B to D. Basically the same as the other problem, only they're using fancy words to jerk you up. It's really fine. So remember what we did in the previous? All we did was we took the velocity times the amount of time it took. That's all we have to do. If you really want to have a formula, you can have a formula. So meters is equal to velocity times time. However, I think it's easier if you just think about what it is. So 6 seconds, they give us 6 seconds. You're going 20 meters per second for 6 seconds, right? So every second you're going 20 meters. So 20 meters, 20 meters, 20 meters, 20 meters. You get it. So all I have to do is 20 times 6, and you can kind of see these cancel out. These seconds cancel out, and you're left with meters. So the units match up. So 20 times 6 is just 120 meters. Nice. Question number 4. This question is about projectile motion. Well, weren't they all about projectile motion? This guy. A ball is projected from the ground level with a speed of 28 meters per second squared. Oh look, information. Let's write that down. Now this graph is kind of whack. Let's make it a little bit bigger, shall we? So it's going at 28 meters per second, so let's write 28. Let's zoom in here. So it's going at 28 meters per second. An angle at 30 degrees to a horizontal as shown below. Alright. So what are they asking? There is a wall at height h at a distance of 16 meters. Okay. So let's go that's 16 meters, and here's the wall. Don't you hate it when there's a wall at 16 meters? It's horrible. Air resistance is negligible. Alright. Let's calculate the initial magnitudes of the horizontal velocity of the ball. Whoa, that's a lot of words. What does that mean though? So what we're trying to find is the horizontal velocity, or the velocity going to the right. So basically this. We have this, where we're trying to find this. Now, if you think about it, in our first problem, what we did was we took the SOHCAHTOA, because this is a triangle, right? So let's draw another triangle down here. So we're trying to find this, and we have this. Now, what we do is we have this angle at 30 degrees, we have this at 28, but we're trying to find the adjacent side of this triangle. We don't know the opposite side. We have the hypotenuse, so the hypotenuse. So let's go through it. So, SOHCAHTOA. We're trying to find our adjacent, so we're going to have to use cosine. So, cosine of 30 is equal to the adjacent over the hypotenuse. We know the hypotenuse to be 28, so we know we have to multiply by 28. So it's just 28 cosine of 30 equals our adjacent, which should be our answer. Let's do it. 28 cosine of 30. 24.2. Remember what we're looking for, 24.2 velocity. So 24. 2 sig figs. 24 meters per second. Alright, next. The vertical velocity. Oh wow. So we found the horizontal velocity, which was this. Now I had to find the vertical velocity, which is this. Okay, let's do that in another color. The vertical velocity. So it's basically the exact same process, but instead of using cosine, we have to use sine, because it's the opposite. We have the adjacent, but we don't have the opposite angle. We're trying to find the opposite. Perfect. Basically the same as this, we can just substitute a cosine for a sine. So it's just 28 times the sine of 30 equals the opposite, which would be our vertical velocity. Switching pens here. Another trick that you may not have known, if you go to your calculator, if you do the up button twice, you can go back here, enter, and then just modify this cosine to be sine. Enter. 14. So our vertical velocity would be 14 meters per second. There we go. Now, I'm not going to lie to you. The next question is quite tough. It took me around 30 minutes to figure out. But I'm going to explain it to you so you don't have to spend 30 minutes figuring this out. So 4B, the ball passes over the wall. Determine the maximum height of the wall. Okay, so this is super tricky. Here's our analogy. The ball just barely passes over the wall. So we know that the ball will be here at some point. And discretion, just a little bit. So we have to find out how high this wall is. Now, if you think about it, this wall, think about it as a triangle. Now, this is 16 meters, as per we already know. And we just now found out that the horizontal velocity is 24 meters per second. So we know that this is going at 24 meters per second. So, using our logic, around what time in this will the ball just be over the wall? Now, that might be really hard to some people, but if you go back, remember thinking here, the range of the golf ball, we took our time and we multiplied it by our velocity, right? So we're going 20 meters per second here, 20 meters per second here, every second. So if we use that same principle, but down here, we're going 24 meters a second. So it would be going 24 meters. This would be 1 second. This ball would travel this amount of time. So it's going to pass over the wall in less than a second, right? But what time exactly will it pass over? That's 16 meters divided by 24 meters. Do you see where this time is coming from? It takes 24 meters. It takes a second to go 24 meters. How many seconds will it take to go 16 meters? So, if we do that as a proportion, so we know that it takes 24 meters to go 1 second. But how many seconds does it take to go 16 meters? 24 times s, so 24s equals 1 times 6 is 16. 24 is just 16 over 24. Our meters over the meters it takes. So 16 divided by 24, if you just simplify it down, 16 divided by 8 is 2. 24 divided by 8 is 3, 2/3. It takes 2/3 of a second for this ball to pass over the wall, to just be over the wall. 2/3 of a second. Now, using that knowledge, 2/3 of a second, we can do a Suvat equation. Before, we couldn't do a Suvat equation because we didn't have time. We didn't have another variable. We were missing 2 variables. Now that we know that it's a second, we can do the Suvat equation. So let's see. let's see what we have. The ball just passes over the wall, determine the maximum height. We're trying to find the height. We're trying to find S. So, S-U-V-A-T, Suvat. S, that is what we're trying to find. Now, we have our time. Remember? We just did that entire thing. 2/3. That's our time. The ball will be over the wall at 2/3 of a second. 2/3 of a second. Our acceleration everywhere will be negative 9.81 meters per second squared. Checking back in the problem, it doesn't explicitly state that it's 10 meters per second. So if it doesn't state that it's going at 10 meters per second squared, we're going to write it at 9.81 meters per second, just to be safe. Now our U and our V, that's kind of tricky because our ending velocity, we don't really know. We don't know what the velocity of the ball will be at this point. But we do know what the initial velocity is. So if we look back at our original point, what's our initial velocity? The initial velocity up, because we're dealing with height. So if we look here, we did find our vertical velocity at 14. So we already know that it's going 14 meters per second. So initially it's going 14 meters a second, and we don't know V. Using our trick, look for an equation that doesn't have V. There it is. Well, look, it's super convenient because we're trying to find S as well. So S equals UT plus 1/2 a t squared. Now, if we plug in the variables, S equals U, which is 14, times T, which is 2/3, plus 1/2. The acceleration is negative 9.81. Remember, negative because it's going down. Time is 2/3 again, squared. Now, we could simplify this, or you could just put everything straight into your calculator, which is way easier. So, let me show you something that some people may not know. You could actually put fractions into your calculator. You go to alpha, y equals, and then enter. And then you can put a fraction in. However, you did it incorrectly because you want to go 14 first, and then you want to put it in. Well, it's 14 times. Don't forget 2 times. And 2/3. So we're doing 2 divided by 3. Next, plus 1/2. So plus and 1/2 is just 0.5. So you can just write 0.5 times negative 9 times negative 9.81 times a negative 9. Math be like, okay, I'll just tell you the answer. If you do everything, if you do all of this, your answer will come out, I promise you. If your calculator is not a potato like mine is, I promise that you will get the maximum height of the wall, which is 7.153333333333, rounding to 2 significant figures, 7.2 meters. 7.2 meters. So doing all of that work, 7.2 meters. Here, the wall, 7.2 meters. That was a tough one. Alright. Nice. We're on to the last page. Question number 5. This question is about projectile motion. What's new? Nothing. So, let's go through this problem again and write what we know. So, a ball is kicked at an angle to the horizontal. The diagram below shows the position of the ball every 5 seconds, 0.5 seconds. That's important. So, This is when the ball is 0, this is when it's 0.5, this is when it's at 1 second. We should probably write that down. So this is when the ball is at 1 second. 1.5, 2 seconds. 2.5, 3 seconds. 4.5, 4 seconds. 4.5, 5 seconds. Cool. So this entire trip takes 5 seconds. Good to know. Let's keep that in mind. Let's continue reading. The acceleration of free fall is 10 meters per second. Correct. There we go. Now we save ourselves a lot of time with all those pesky 9.81 decimal places. So we know negative 10 because I like to put down is negative, up is positive. Good. Air resistance may be neglected, as always. Alright. A1, or I, whatever. The horizontal component of the initial velocity. Whoa. Okay, hold up. Words. Horizontal. Okay, so this way, or this way. Of the initial velocity. Okay, so when it's starting here, right? So we're trying to find the horizontal component. Now that might take a second, right? But if we think about it, the initial velocity horizontally here is the same as it's here, as it's here, as it's here, correct? Because a bullet shot is the same as a bullet drop, correct? So velocity here is going to be the same, here's going to be the same, here's going to be the same, here. So we can take any of these points to find out this. We don't have to be 0, 0, because 0, 0 would just be 0. Now, let's take this last point. So, if you read it, the horizontal displacement is 40 meters. So this ball is going 40 meters to the right in 5 seconds. It's going 40 meters in 5 seconds. Now, we gotta simplify this down because that's not a velocity, that's just a term in another term. So, how do we do that? Simple. 40 divided by 5, which all of you should know if you're not in preschool, 8. 8 meters per second. That's our horizontal velocity. Here's going 8 meters per second, here's going 8 meters per second, and so on and so on. And you can kind of see that here too. If this is 10, then this would be 5. If you can zoom in. This is 10. Then this would be 6, 7, 8. At 1 second, he's going 8 meters. So our statement is correct. He's going 8 meters per second. Now, let's write that down here in another sense so we can keep track of it. 8. Next. Oh, we knew this was coming. The vertical component. So now instead of going from here, we have to go up. Now the thing about vertical velocity is it's not like horizontal. For the horizontal, there was nothing acting upon it except air resistance, yet air resistance is negligible. For vertical velocity, you have gravity. And gravity is always going to be pulling down on the vertical velocity, so you can't accurately rely upon just taking, let's say, this point and dividing by this. So you can't just rely on taking 20 and dividing it by 1, because 20 divided by 1 would just be 20. 30 divided by 2 is 15, as you can see is changing. So that's not reliable at all. So what we have to do in this situation is use SUVAT. So let's take another piece of paper and write down SUVAT. S-U-V-A-T. Now, let's see. What are we trying to find? We're trying to find the vertical component of the velocity. Initial velocity. So we're trying to find U. Now, initial velocity, that's when U is right. So we're trying to find when it's right here. So our displacement was just 0. Because right here, it's going 0, 0. It's nowhere. Our velocity ending up, we don't know what that is because we don't even know where we're starting at. Our acceleration, always negative 10 meters per second. Right, meters, always write in your labels because Mr. Button will eat you if you don't write in your labels. Now your time is kind of wonky because your time of the entire point. If you just take the time of one, it won't work because you're taking the average of all of these points as I showed out. So 20 divided by 1 is 20. 30 divided by 2 is 15. As you can see, it's changing. So you want the average of all of these times. So you want the last time, which is 5. 5 seconds. 5 seconds. That was just a normal equation. And I'm not going to lie, this question here, this took me a while as well. This took me another hour to figure out. V. So this doesn't have V. This is what we're trying to find. So the displacement equals the initial velocity times time plus 1/2 times the acceleration time squared. This is actually a pretty easy problem. If we substitute in 0 equals, and we're trying to find, times 5. You don't need me commentating this. This is just simple math. Alright, you really don't need to know this. I mean, you do. This is math. So 5u negative 5 times 25. 5 squared. I swear I can do math. Oh look, divide by negative 5, divide by negative 5. These cancel out, these cancel out. U equals 25. Magic. Wow. That's great, isn't it? So, our velocity upward, our vertical component is 25. 25 meters per second. That's our velocity. That was quite difficult for me. Not for you, though. You got this in the bag. Alright, our last two questions. Come on, it's not that hard. The magnitude of the displacement after 3 seconds. Interesting. So, after 3 seconds, that's right here. So we're trying to find, what are we trying to find? The magnitude? The magnitude of the displacement? So remember how Mr. Tefetna was talking about vectors? And vectors have two parts, the magnitude, what this is, and the angle. So the magnitude is basically like the length, the meters, the distance. So we don't have to do anything fancy here. So let's look here, 30. It's going, if we bring this down here, this is at 24 meters. And if we bring this to the right, this is 30 meters. So let's bring this point over here so we can visualize it more easily. So this point down is 24 meters, and to the right is 30 meters. So now this is just a simple Pythagorean theorem problem. So we're trying to find the magnitude of these two vectors, so basically the average of these two. So you just need to do 30 squared plus 24 squared equals c squared, which is just the square root of these. Because if you look at it here, well, this isn't a really effective way. Oh, 30 is backwards. The 30 would be here. Well, it wouldn't be. It would be facing this way. But you can see, this is the hypotenuse. We're trying to find the hypotenuse here. So, taking our calculators. So, we're trying to find the square root of 30 squared plus 24 squared. 24 squared? Yep. Enter 38.4. 38 meters. So, our magnitude at 3 seconds is 38 meters. Alright guys, last problem, and it's not really a problem, it's just, on the diagram above, draw a line to indicate a possible path for the ball if air resistance were not negligible. Oh, so, for all the other problems, air resistance was negligible. Now they're saying, what happens if it's not? Let's draw this in a different color, for time's sake here. Cyan. So, air resistance, if you know a little bit about air resistance, it's just resistance. So, it's not going to go as high, and it's not going to go as far. So that's basically all you have to do. Just draw anything under here. Just nothing wacky. Just like, there you go. It's not as high. And It's not as going as far, so it's here and here. And also, I kind of did it bad here, but you kind of make it asymmetrical, because when you're just going this way, it's going to have more air resistance because it's actually pushing. So it actually more look like that or something. But anything here doesn't really matter as long as you have it down. Alright, so that's basically it. Now, if you want, a lot of people are probably going to skip through all of this, but if you stuck through the entire thing, good for you. You kind of actually understood what was going on. But I put a link where you can just look at the answers after. You don't have to shuffle through. So I'll just go through them really quick. Okay, for all the people skipping to this point, here's an overview of the answers and a really, really quick explanation of them. So for question number 1A, it states, at point P, the diagram above, draw arrows to represent the acceleration and the velocity. Quick answer is, the acceleration is just it going down at negative 10 meters per second squared, or negative 9.81 meters per second squared if you really want to be precise. And the velocity never changes when it's going horizontally. Bullet fired versus bullet dropped, the exact same thing. Next, question number 2. Stands at the edge of a vertical cliff, throws a stone upwards at 60 degrees to the horizontal. Alright, A. The maximum height reached by the stone. This is just a trigonometry problem. You are looking for this point right here. So what you need to find first is the horizontal velocity, which is 6.8 meters per second, which you can find out using the SO of the SOHCAHTOA and doing some trigonometry here. Then, using this, substituting into a Suvat equation, 6.9, where the top velocity is 0, final velocity is 0, initial is 6.9, acceleration is negative 10 meters per second, using this formula to get 2.4 meters. So the maximum height reached by the stone is 2.4 meters. Next, the horizontal distance, different from the vertical distance because horizontal up versus to the right, not as hard. All you have to do is first find the horizontal velocity, which instead of doing the so, you do the ka, because you're trying to find the adjacent, not the opposite this time. So a times the cosine of 60, which is just 4. And then, because it's going 4 meters per second, you multiply that times the number of seconds, which here and here it states as 3 seconds. 4 times 3 is 12. It's going 12 meters over 3 seconds. Next, so previously it states structure of a golf course. Number 4, calculate the maximum height reached by the golf ball. Basically the exact same as 2A, only this time you don't have to calculate it. They already give you the vertical velocity, which is at 30 meters per second. So doing some more math, the initial velocity is 30 meters per second. You're trying to find it at the height here, which is at 0. Acceleration always negative 10. You're trying to find the distance. Using this formula here, you get 45 meters. Next, find the range of the golf ball. Exact same thing as 2B. The movement in meters is equal to the velocity times the time. So you're going 20 meters per second over the course of 6 seconds, which you can also see here. 20 times 6. 20 times 6 is 120, and you can see here the units cancel, seconds cancel, leaving you with meters, 120 meters. Number 4. 1A, calculate the horizontal velocity of the ball. Now this is a really wacky problem, so what you're trying to find is this. You're trying to find this velocity of the ball. Long story short, you need to first find the cosine, which is the adjacent right next to it, using the 28 that they give to you. Just like in 2A, plugging these into a cosine equation, 28 cosine of 30, you get 24. More cosine trigonometry here. Next, the vertical velocity of the ball. Exact same thing. Instead of using the cosine, you use the sine because you're trying to find this, the vertical velocity of the ball, which in this case would be the opposite sine. So sine over the opposite over the hypotenuse. 28 times the sine of 30 equals 14 meters. Now 4b was super hard. Now condensing down a lot of the math, if you really want an in-depth explanation of 4b, which I highly recommend you do because this is actually a super dense problem, go back to, in the link there's going to be a description of all the times of the problems, and I'm going to explicitly put out 4b for you. Long story short, again, the answer is 7.2 meters. Lastly, for problem number 5, 1a, the horizontal component of the initial velocity, 8 meters per second squared. You just do that by taking 5 seconds, dividing it by how much time it took, the amount of meters that it had, which is 40 meters. 40 divided by 5 is 80. It's going 40 meters in 5 seconds, or 8 meters every second. 25 meters per second. Here, this is kind of different as well because it's using suvat mostly, because you're taking the entire time of it. So plugging it in, the distance of this, because you're trying to find the vertical component, would be 0. You're trying to find the initial velocity. You don't have the final velocity. Acceleration is always negative 10 meters per second, and the time is 5, because you're trying to find the average of all of these. 5 seconds. Using this formula, condensing it down, 25. 25 meters per second squared is your velocity, vertical velocity. Magnitudes of displacement after 3 seconds, if you look at the point 3, it falls on 24 meters horizontally, and it falls on 30 meters vertically. 30 squared plus 24 squared, square root of that is your answer, because you're just basically finding the magnitude or the hypotenuse of this right triangle, which is 38 meters. And then lastly, for 5b, on the diagram above, draw a line to indicate a possible path for the ball if air resistance was not negligible. So for all the other problems, air resistance was negligible just to make everything easier. However, in 5b, they want you to hypothesize what it would look like with air resistance. So basically, it wouldn't go as high and it wouldn't go as far, and also would be more asymmetrical. Now, I hope you guys learned a lot over this. It's one of my first videos, and I don't know if you understood it. If you kind of didn't understand it, talk to me during class and try to clear it up for you. There you go. Happy physicsing.